Welcome to the second lecture in the series on tensor analysis. In this lecture, we are going to meet a new breed of vectors, which used to be called covariant vectors earlier and are nowadays called covectors, although the old name still persists in old textbooks. We will see why such things exist and also ask ourselves a question as to why we had survived through high school and even first few years of college without ever learning about these things. But before we do that, let us just recapitulate the basic points of what we talked about in the first lecture. In the first lecture, we mostly talked about vectors. In particular, we stated that vectors are objects which are described by a number of components. That number can be 3 in the case of ordinary 3D vectors, or 4 or n in an n-dimensional space. Now these components transform in exactly the same way as coordinates do or coordinate differentials do. So just to quickly recapitulate some basic points, you could have vectors under rotations, which are the usual vectors that we talk about. Under a rotation of coordinates, the ith component of the position vector, the ith coordinate, becomes x prime I, which is equal to rij xj, where rij is the ijth element of the rotation matrix. Note that here we are using the summation convention which Einstein gave us, that is, repeated indices are summed over. So when I say rij xj, I actually mean sum over all possible values of j of rij xj. In other words, ri1 x1 plus ri2 x2 plus ri3 x3. Now under such a transformation, vectors would transform in the following manner. The ith component of the vector will transform into a prime I given by rij aj. So all you do is replace the x's by a's and x primes by a primes and you are done. In addition to just this transformation rule, we have to bear in mind that rotations have some special properties. In particular, they are orthogonal transformations which preserve the length of the vector, and as a consequence, they obey the relationship rij rik, once again sum over I implied, equals delta jk, which is just another way of stating the matrix level fact that R transpose R is identity, or simply put, the transpose of the matrix R is its inverse, so R is an orthogonal matrix. The next example that we talked about in the last lecture was that of Lorentz transformations, where you talked about space-time coordinates in 4 dimensions. My space-time covector became a collection of 4 numbers x0, x1, x2, x3, that is ct, x, y and z, and under the Lorentz transformation, the x is changed to x primes, and x prime mu is given by lambda mu nu x nu. Please note the rather peculiar placement of the indices. As we promised in the last lecture, we are going to explain the rationale behind such a choice in this lecture. Once we meet covectors, the reason for writing indices this way will be clearer. But anyway, here also the sum over nu is implied. So this is really lambda mu 0 x0 plus lambda mu 1 x1 plus lambda mu 2 x2 plus lambda mu 3 x3. And associated with the Lorentz transformations is the concept of a 4 vector, which is just a vector under Lorentz transformations. So this is a physical object which can be described by a bunch of 4 numbers a0, a1, a2, a3, which transform exactly like the coordinates, so that a prime mu becomes lambda mu nu a nu summed over all nu. And here there is an error. The nu should actually be written as a superfix. It should be lambda mu nu a upper nu. Now just like rotations leave the length of a vector unchanged, Lorentz transformations leave invariant a quantity which is called the invariant interval, that's x0 square minus x1 square minus x2 square minus x3 square. And this led us to introduce a particular matrix eta, whose components eta mu nu were basically plus 1, minus 1, minus 1 and minus 1 down the diagonal. It was a diagonal matrix, so all of diagonal terms were 0. And the invariance of the interval essentially led us to this particular restriction on the coefficients of the Lorentz transformation matrix. Eta mu nu, lambda mu rho, lambda nu sigma must be equal to eta rho sigma. Once again, sum over mu and nu implied. And this can be written down in the form of a matrix equation, which is often an easier one to understand or handle. And if the matrix formed by these coefficients lambda, mu, nu, etc. is called L, this equation turns out to be the same as the matrix equation LT eta times L equals eta. Having cut our teeth on these simpler but very important special cases, we moved on to the case of vectors under general coordinate transformations. In general, you could have a coordinate transformation from x1, x2, xn in an n-dimensional space to a new bunch of coordinates x prime 1, x prime 2 up to x prime n, where the new coordinates could be some nonlinear but invertible, at least locally invertible functions of the original coordinates. And the important issue here was that these transformations could in general be nonlinear. However, it turns out that although the actual equation transforming coordinates may be nonlinear, this always leads to a linear transformation among differentials. dx prime I is always del x prime I del xj dxj. Once again, Einstein summation convention is being used here, and we defined a vector in n dimensions under general coordinate transformation to be a bunch of n numbers a1, a2, a3 up to an, which under this coordinate transformation become a prime 1, a prime 2 up to a prime n, where a prime I is given by del x prime I del xj aj. Once again, all you do is change the x's to a's and x primes to a primes and you are done. We have been talking about the Einstein summation convention as part of all the examples that we have talked about so far. Let me just remind you that the convention says that if an index is repeated, you are supposed to sum it over, but with an important caveat. If you are using a notation where you use upstairs and downstairs indices, as we did in the last two examples, you would actually have to adopt that additional rule that you only sum up over dummy indices if they appear once as a suffix and again as a superfix. Indeed, expressions where a particular index is repeated twice as superfixes or twice as suffixes are strongly frowned upon and should not really be part of any legitimate expression. The reason for this will become clear soon. There's just one catch here, of course. When we discussed rotations, we used suffixes throughout. We never use superfixes. And there, this particular part of the convention does not apply. If you just repeat an index, it's summed over. There is no upstairs downstairs rule there because you don't use superfixes there at all. Now, why don't you use superfixes for rotations? And why do you use them for the other transformations? We will answer this very soon when we introduce the next kind of important object on our list, which are covectors. As a prelude to the introduction to covectors, let us take a look at an old friend from high school, the scalar product or dot product of two ordinary vectors. A dot B, let me remind you, was defined either as magnitude of A times magnitude of B times cosine of the angle between them, or as the sum AI/BI. Just in case you have not come to terms with the Einstein convention yet, let me remind you that AIBI really is A1B1 plus A2B2 plus A3B3. Once again, the upstairs downstairs rule does not apply here because here we are only using suffixes, no superfixes. Now the question that we have for you is, it's fine to call this a scalar product, but exactly why is this a scalar? In other words, when I do a coordinate transformation, A1, A2, A3, the components of the vector A changes to A'1, A'2, A'3. And the components of B changes to B'1, B'2, B'3. Of course, AIBI changes to A'I, B'I. That is A'1, B'1 plus A'2, B'2 plus A'3, B'3. Now, is this a scalar? It is a number, no doubt. But it is going to qualify as a scalar only if it is an invariant under rotation. That is, only if you can carry out a rotation and the resulting expression does not change. So let us see what our coordinate transformation rule for vectors actually tell us about the quantity AIBI, how that is going to transform. Since AIs and BIs are components of vectors, we know that A'I will be Rij Aj, where Rij are the coordinate transformation matrix elements, and B'I will be Rij Bj. So what exactly is A'I B'I? Now here is the beauty of the summation convention. You don't really have to write the sigmas, you just have to bear in mind that they are there, and many of the manipulations involving sums, such as changing the order of summation, etc., become sort of trivial in this notation. So A'I B'I is actually equal to Rij Aj, simply because A'I is Rij Aj, times Rik Bk. This is one thing you have to be very careful about. You cannot write B'I also as Rij Bj, because you do not want to confuse this summation index, the one which gives us B'I, with the summation index which gave us A'I. So Rij Aj, Rik Bk. You could have equally well called this Rik Ak, Rij Bj, or for that matter, Ril Al, Riq Bq. The dummy indices can be written as anything you want, except that you should not confuse two dummy indices which are different by using the same letter. And of course, you cannot use some other index which is already being used. But the next step would be, move the Rik ahead of the Aj. This looks simply like commuting two numbers. After all, Rik and Aj are both numbers. So all you are doing is changing the order in which you multiply them. But the notation actually also implies that now you are going to do the sum over I in Rij, Rik first, and then multiply the result by Aj, Bk, and then sum it. Now, because of the orthogonality of the rotation matrix, Rij, Rik is delta Jk. So what this expression becomes is delta Jk, Aj, Bk, and that is the same as Aj, Bj, when you sum it over K. Of course, Aj, Bj is exactly the same as Ai, Bi, and this means that under the rotation of coordinates, A dot B changes to A dot B prime, which actually is exactly the same as A dot B. So A dot B really is a scalar. Now this proof, though very simple, is important enough that it merits being examined in a different manner. You could also carry out the same proof using the fact that you could write down the vector A in the form of a column vector and the B vector in the same manner. That is, you could write A vector in this form, A1, A2, A3 as three components written in a column. And similarly, B vector could be written down as B1, B2, B3 in a column. Now, of course, you cannot multiply two column vectors, but what you can, of course, always do is transpose this column vector A to form AT, which is the row vector A1, A2, A3, and then multiply that by the column vector B, and that will give us a 1 by 1 matrix, which is effectively the same as a number, given by A1, B1 plus A2, B2 plus A3, B3, and that, of course, is our dot product. So this matrix version for the dot product is you transpose the first column vector multiply the second column vector, A transpose B. Now under the rotation, what happens to this? A transpose B of course becomes A prime transpose B prime, but the column vector under the rotation of coordinates changes in exactly the same way as the column vector with x1, x2, x3 would change. That is, it gets multiplied by the rotation matrix R. So what you get here is A prime is RA and B prime is RB. And therefore, A prime transpose B prime is RA transpose RB, which using a standard elementary property of transpose of product of matrices becomes A transpose R transpose times RB. And since R transpose R is identity, R being orthogonal, what we get is A transpose identity times B, and that is the same as A transpose B, which is just another way of showing that the dot product of two vectors does not change when you carry out a rotation of coordinates. This rather simple proof actually leads to a very important point. Note that A dot B, which is defined to be AIBI, is a scalar, but it is a scalar only because the transformation matrix R is orthogonal. Now that is a property of rotations, but not all transformations are rotations. If R had not been orthogonal, that is, if X had become X prime equal to Rx, where R is a non-orthogonal matrix, AIBI would not be a scalar. Indeed, it would not even be what is called a well-defined geometric object or a well-defined entity independent of the coordinate system. To see a proof of this in matrix language, let us just figure out what happens to A transpose B when we carry out the transformation X goes to Rx and the vectors automatically change like A goes to Ra and B goes to Rb. Then A transpose B, as before, goes to A transpose R times B. However, a general coordinate transformation is not orthogonal, so R transpose R would not be the identity, and now we will not be able to find out its value if we just knew the original value A transpose B. Of course, if we knew the original values of the two vectors involved, A and B, then we could figure out what they become in the new coordinate system, and then we could calculate A prime 1, B prime 1 plus A prime 2, B prime 2 plus A prime 3, B prime 3. But for this, you would need to know the individual components themselves. Just a knowledge of A1, B1 plus A2, B2 plus A3, B3 or A transpose B in one frame will not allow you to calculate it in another frame. So that is what I mean when I say this particular quantity does not have an existence independent of the coordinate system. So AIBI is no longer a scalar the moment you move away from orthogonal transformations. Even such a nearly orthogonal transformation as Lorentz transformations have the same problem, if you can call it that. Note that under a Lorentz transformation, the quantity which is invariant is not x0 square plus x1 square plus x2 square plus x3 square. It is actually x0 square minus x1 square minus x2 square minus x3 square. And under Lorentz transformations, quantities like A mu B mu, A0 B0 plus A1 B1 plus A2 B2 plus A3 B3 is not a scalar. Not only that, it is not a well-defined object in the same sense as before. If you know A0 B0 plus A1 B1 plus A2 B2 plus A3 B3 in one coordinate frame, you have no way of finding out A prime 0 B prime 0 plus A prime 1 B prime 1 plus A prime 2 B prime 2 plus A prime 3 B prime 3. Unless, of course, you knew the original components of the four vectors involved. Can we then rescue the notion of the scalar product for non-orthogonal transformations? Note that I have written scalar product within quotes here, and there is a reason for that. You will soon see why this is really not a genuine scalar product that we are talking about, but something very similar. Now, as we have already seen, If A and B are both vectors, then under the coordinate transformation x going to x prime equal to Sx, where S is not an orthogonal transformation, so that STS is not the identity, then the quantity A transpose B is not a scalar. If on the other hand, A transform differently under x going to x prime equals Sx, let's say A goes to TA, where T is a related matrix to S but not the same matrix as S, while B is a vector, then can we find out a scalar product which is really a scalar between A and B. Note that the reason why I have put scalar product within quotes here is that a scalar product really is between two vectors. The moment you say that A is going to transform differently, you are not really talking about a product between the same kind of elements. You are talking of a different breed altogether. The question is, can I at least find a kind of object which transforms in a manner such that AIBI or A transpose B actually is a scalar? And the answer is that there is such a kind of object, so that we can rescue the scalar product, at least in this sense, even for non-orthogonal transformation. Now that we know that A goes to TA and B goes to SB, what happens to A transpose B? Very simple, A transpose B will go over to A transpose times T transpose SB, and this will be a scalar. That is, it will stay the same if T transpose S is the identity. That's sort of straightforward. That means T is nothing but S inverse S transpose or S transpose S inverse. So, in order that we can form a scalar by the action of A on B, A has to transform differently from B, and the transformation rule must be this. Under x going to Sx, A must go as S transpose inverse times A. Whereas the matrix which multiplies the coordinate column vector to give you the new coordinate column vector is S, and that is the same matrix that is used for vectors. For this kind of object which produces scalars out of vectors, the transformation matrix must be S transpose inverse. So while components of a vector transform like the coordinates, the components of objects which act linearly on vectors to give scalars actually transform oppositely, so to speak, because there's an inverse involved. You have studied in linear algebra, you would know that such objects which map vectors to scalars are actually called dual vectors. So this is really not the inner product or scalar product of two vectors, is the action of a dual vector on an original vector which gives you a scalar. And the dual vectors have to transform in this manner. A goes to S transpose inverse A. Now this looks rather ugly, but it becomes neater and actually justifies the term oppositely much better if you were to think about A slightly differently. The reason why this transformation rule looks so ugly is that we are thinking of A as a column vector. Whereas, since A's role is to give a number out of a column vector, that is B, it's much better actually to think of this as a row vector. In which case, of course, you will not have to transpose it first to make it act on B. You could just say A acts on B. In other words, the ideal thing to use if we were using matrices to represent our vector components, row matrices or column matrices, you would actually be using the transpose of the matrix that we are using here. You would be using rows, and for the transposed one, it's easy to figure out that the transformation rule would have been A goes to A times S inverse. And this is where the oppositely becomes obvious, whereas B transforms by getting S to act on it on the left, the row vector A transforms by getting S inverse to act on it on the right. So now we see that contrary to what we had learned in our high school, there are actually two different kinds of 3-component objects in 3D or n-component objects in ND, which are both vectors in some sense. Under the transformation x goes to x prime equal to sx, vectors would transform like b going over to sb exactly the same way as coordinates, whereas this new kind of object, which we are going to call a covector, which is just another word for dual vector, transforms according to the rule A goes to ST inverse A. Once again, let me remind you that this ugly ST inverse factor is there only because you are using column vectors to represent them. If you were to use row vectors, that is the transpose of this A to represent them, the rule would have been simply A goes to A S inverse. Now, all this is fine when we talk in terms of the full vectors, either as column vectors for vectors and row vectors for covectors. The problem begins when we want to talk about the ith component of this. Why is that a problem? Because if we were to stick to the standard convention that we only use suffixes to write indices, then from the notation there would be absolutely no way to distinguish between a vector and a covector. The ith component of a vector would be called bi. The ith component of a covector would also be called ai if a is the label for the covector. Now, of course, one thing we could always do is adopt a convention where we use different letters, maybe letters from different alphabets altogether, to denote vectors and covectors. You could use Latin letters for vectors and Greek letters for covectors. You could use Latin letters for vectors, Cyrillic letters for covectors. You could also use a convention like letters from the beginning of the alphabet like A, B, C, D are going to be used for covectors, and those from the end of the alphabet like U, V, W would be used for vectors. But all this would become rather confusing, and very often you will see that the same object can come in two avatars, a vector avatar and a covector avatar. Having to change the notation for that having to use an entirely different letter to denote it, depending on whether you're talking of a vector or a covector, will become very, very painful. So instead of doing that, we use this simple convention that we use both suffixes and superfixes for indexing. And so the ith component of vector b is denoted b upper I. This is something we had already met in the last lecture, but there we had not explained why you have an upper index. We just said that that's a convention. Now we know. Whenever you're talking of non-orthogonal transformations, you have to clearly distinguish between vectors and covectors. And then, in component notation, the ith component of a vector b will be written with b with an upper index I, and the ith component of a covector a is denoted with a lower index I. And once we adopt this convention, we see that a lower I, b upper I is actually a scalar. That's actually what we were calling A transpose B earlier. And in components, that's just A1 B1 plus A2 B2 plus A3 B3 plus up to A and B and summed over. Remembering, of course, that A1, A2, A3 are covector components and B1, B2, B3 are vector components. This actually is the origin of that caveat in the Einstein summation convention. You only sum up over dummy indices when the index is repeated once as a suffix and once as a superfix. Then you get a well-defined object if you do that. If you had AI, BI where I were both superfixes or both suffixes, the resulting object would not have any frame-independent existence. You would not be able to compute the new value of that object in a new frame if you just knew its value in the old frame. So such things are definitely a no-no. One point which you must have pondered by now is how come we did not learn about covectors in high school? The answer simply is, if S really were an orthogonal transformation, S transpose inverse would be nothing but S itself. So under orthogonal transformations, there is no way to distinguish the behavior of a vector from the behavior of a covector. Both kinds behave in exactly the same way. Which is also why, under orthogonal transformations, the dot product of two vectors is actually a scalar. So why didn't we meet covectors before? The answer is, in high school and in fact even a long time after that, the only vectors and scalars we were talking about were actually vectors and scalars under rotations. And under rotations, vectors and covectors behave exactly the same way. There is no distinction. In fact, you do not have the concept of a covector if you are just dealing with orthogonal transformations, which by the way includes, besides rotations, reflections as well. Also note another point, that AI, BI, where the two i's are in different positions, suffix and superfix, is a scalar, as we have said. How many indices does a scalar have? The answer is none. So in a sense, the indices sort of kill themselves off. So AI and BI individually had one index each, one covariant index and another so-called contravariant index. We have not used that nomenclature yet, but we will explain what that means soon. To avoid that kind of terminology, let's just say one downstairs index and one upstairs index, and they cancel each other out in a process called contraction. In other words, what has happened is you started with two objects which are indices, now they have been contracted, that's a technical term for this, and now you have no indices left. So repeated suffix-superfix pairs contract and essentially go away. Now that we have understood the rationale behind using suffixes and superfixes for components, as well as the reason behind the upstairs-downstairs restriction in the Einstein summation convention, let us try to see how that applies to the case of coordinate transformations themselves. We had so far talked about a general linear coordinate transformation. X goes over to x prime equals Sx. This of course is written in the matrix notation. If we want to write this in component notation, I would write this as x prime I equals Sij xj, where Sij of course is the ith row jth column element of the matrix S. But note that we denote the ijth element of S in this particular peculiar fashion, where I is written upstairs, the first index, and j, the second index, is written downstairs. So the indices go from top left to bottom right in a diagonal. We have already met this convention before when we talked about Lorentz transformations. Let me point out that the reason why we do this is as follows. X prime I has I as an upstairs index simply because coordinates are the prototype vectors, and vector indices we have written as superfixes so far. And in order to match the position of the indices on both sides, the I or the right hand side should also be upstairs. So the row index of the matrix is written as a superfix. What about the column index? Now the column index has to be summed over. That is a standard rule for matrix multiplication. Now, while we have actually justified the rule or restriction of summing up over only upstairs and downstairs indices in the case of forming a scalar out of a covector and a vector, and we do realize that that rule, strictly speaking, does not apply here, because here we are not really trying to form a scalar product out of a pair of old objects. What we are doing here is trying to figure out what the object will become or how the object will be described in terms of new coordinate system. But still, once we have made this rule, we do not really want to relax it. So we want to insist on this upstairs-downstairs rule for all summations as long as we are using superfixes and suffixes for different kinds of objects, which means as long as we are using non-orthogonal transformations. And in order to conform with that, we write the j index downstairs. As a result, the transformation rule for a vector, when b goes to b prime equal to sb, becomes, in the language of components, P prime I, where I is a superfix, equals Sij Bj, where the I and j indices are written from the top left to the bottom right. Now, what is interesting is that we actually apply the same ideas when we try to figure out what the transformation law for a covector is going to look like in terms of components. Remember, we had already said that if you thought of the covector as a column vector, then the transformation rule would go like A going to A prime equals S transpose inverse A. And in order to distinguish from a vector, we write a covector with downstairs indices. So A prime lower I in terms of components will become S ij aj. Note that we use the same letter S to denote this, but the placement of the indices is very different. So here I, the first or the row index, is written downstairs to match with the I index on A prime I. And in order to ensure that the upstairs downstairs rule for summation keep on working, here we write the j index, the column index, upstairs. So here the indices go from bottom left to top right. So it's the other diagonal, different one from the one which we used for the coordinate transformation or for the vector transformation. Note that when I write Sij with the indices going in this way, we are not really talking about elements of the matrix S, despite the fact that we use the same letter to denote it. We are actually using the elements of the matrix S transpose inverse. So once you adopt that convention, you can actually write transformation laws for vectors and covectors very similarly. It is just the way in which the indices are written that makes the difference. I must warn you that this takes some getting used to, and if you place your indices wrong, your expression might end up becoming meaningless. But once you get used to this way of writing things, you will find that it's actually very convenient and helps you to quickly write down transformation equations for various kinds of objects without having to worry too much about what the underlying matrix really is. The fact that the placement of the indices actually makes a difference as to which particular matrix you're really talking about, whether you're talking about S or about S transpose inverse, can lead to some potential confusion. Also, let me warn you that if you are using a badly published book, sometimes the publishers may not have spent enough time or effort on the font faces, and they may not end up giving you a proper placement of the indices. So it may become a bit confusing that way. Having said that, this particular kind of notation is really rather convenient in the long run. So my suggestion is try to get used to it as much as you can. Well, let me help you along on the way. We will now look at two very important results, which are basically simple matrix results rewritten in the terms of this kind of notation. For the first one, we begin with the obvious statement that S transpose inverse multiplied by S transpose is the identity matrix, so that if I look at the ijth element of the matrix on both sides of this equation, I will end up with a statement that sum over k equal to 1 to n of the ikth element of S transpose inverse times the kjth element of S transpose is actually ij. Note that here we are not using the summation convention. We have explicitly written down the sigma symbol, and as a result we have foregone the need for writing upstairs and downstairs indices and a contraction rule like that. But we will now try to rewrite this using the summation convention. Note that S transpose inverse as ikth element is actually Sik, where I is written bottom left and k is written top right. Whereas S transpose as kjth element is actually S as jkth element, so it has to be written with j on the top left and k on the bottom right. So putting these two things together, I get Sik Sjk, where the summation is over k, which naturally has come as a superfix in one term and a suffix in another. And the result is delta ij, the ijth element of capital I. But note that now, in keeping with the position of the free index on the left, the I is downstairs on the left and j is upstairs. We have maintained the same index position on the right. So when I write delta ij, I is written downstairs and j is written upstairs. Let me also point out that in this case, I have written I and j on the same vertical line. So here, from the notation, it will be impossible to tell which one of them is a row index and which one is the column index. And the reason why I could do this and get away with it is simple. The identity matrix happens to be symmetric. So in this case, which one is row, which one is column does not matter. I can safely put the indices on top of one another. Now what I have been warning you about bad typography, in some textbooks, the typography is such that even for the S matrix, you will find the two indices written on the same vertical line, which of course is absurd because now you have no way of knowing whether you are talking about the S matrix's element or S transpose inverse matrix's element. Let us now try to find out one more similar relationship. Here we start with an equally obvious statement that S transpose times S transpose inverse is equal to identity. And I will let you figure out exactly what is going on here in terms of the matrices coefficients that I have written down in green here. But ultimately what you get is Ski, where k is on the top left, I is on the bottom right, times Skj, where k here is bottom left, j is top right. This sum over k is actually equal to delta ij once again. Note that both these equations are really rather easy to remember. You are summing up over upstairs and downstairs indices for two different coefficients s. And what is important is that they are either both column indices or both row indices. That is, they are either both in the first position or both in the second position. Once you do that, the resulting sum is going to be delta with the other two indices stuck in the right positions. What that should be can be simply found out by invoking consistency in position between the left and the right hand side of the equation. So frankly, despite the fact that these two equations look slightly tricky, especially remembering which index goes where, they are actually quite easy to remember and easy to use. Let me demonstrate how simple it is really to use these relations by showing you once again how to prove that the so-called product between a covector and a vector is actually a scalar. So let us start with a lower I, b upper I. Of course, a lower I means this is the ith component of a covector and b upper I is the ith component of a vector. Since there is a summation convention in place, it's really not one component, it's a dummy index. Anyway, under a coordinate transformation, a lower I goes to a prime lower I and b upper I goes to b prime upper I. But a prime I is Sij Aj with I and j going in this direction, the indices, this kind of diagonal from bottom left to top right, whereas b prime I is Sik Bk where the indices go like this. Let's pull the Sik's to the front. Simply by using the fact that they commute with all the numbers sitting here, let me point out once again that what we are really doing here is insisting that the sum over I be done first. Note that here I is upstairs and downstairs as a dummy index, so the summation is implied, and it's sitting in the first position for both. So according to the rule that we have just worked out, this has to be delta jk. So the full thing is delta jk aj bk. And using the fact that delta jk summations are really trivial, you can sum up over k and end up with aj bj. Of course, aj bj is exactly the same as ai bi. And so what we have established is that under a coordinate transformation, this result of multiplying vectors and covectors term by term and adding up, forming a1 b1 plus a2 b2 plus a3 b3 all the way up to an bn, does yield a scalar. I hope you are convinced by now that under a general coordinate transformation, a non-orthogonal coordinate transformation in n dimensions, you would have two different kinds of n-component objects, both of which look like vectors. One of them is a covector, the other is our original old friend, the vector. Now, there is a bit of a puzzle about the nomenclature of these things, especially the slightly older nomenclature that you will still find in many textbooks. What we are calling covectors here used to be called covariant vectors, and what we are calling just plain vectors used to be called contravariant vectors. Now, the real question is, vector components, as we have seen, transform like coordinates. But the word contravariant actually means things which vary oppositely. Contra, of course, means opposite. So covariant vectors are vectors which vary similarly. Contravariant vectors are vectors which vary oppositely. Now this is a nomenclature which has often led to a lot of confusion. It does seem that it would be more reasonable to call vectors whose components transform like the coordinates covariant, and call the covectors whose components transform in an opposite kind of way the contravariant entities. Instead of that, vector components are called contravariant and covector components are called covariant. I have actually already used that terminology once before in this lecture. As I said, this is old terminology, and so I would try to avoid using that most of the time, but old habits do die hard. The answer to this apparent fallacy in the nomenclature lies in thinking in terms of the basis vectors. So those of you who have done linear algebra would definitely know this, that there are special vectors or a set of vectors in a linear vector space which can be used as a sort of building block of that linear vector space. All you have to do is combine them linearly, multiply them by coefficients, and then add up the results to get an arbitrary vector in the space. So an arbitrary vector x could be the position vector itself, would have components x1, x2, x3 in terms of the basis vectors e1, e2, e3, and the vector itself actually would have been x1, e1 plus x2, e2 up to xn, en. And once again, just to ensure that the upstairs downstairs rule for the summation convention is followed even here, we write xi with the upper index and ei with the lower index. By the way, this also solves the puzzle as to why vectors end up getting the upper index for their components. After all, we do naturally tend to write indices as suffixes. So why is it that vector components, which should be more natural things, or at least should come first in the logical order of things, are the ones which end up with an upper index? The answer really is that it is the basis vectors which you focus on first, and the basis vectors are labeled in the standard usual ways, that is, they are labeled with suffixes 1, 2, 3 and so on. And then in order to ensure that the upstairs downstairs rule of the summation convention is properly followed, we write the components xi's with upper indices. So the numbers that we have been dealing with so far, the components of the vectors, are nothing but the numbers that you would have to use in the linear combination as factors for the ei's to yield the particular vector x. Now the whole point is, this vector x is actually independent of the coordinate system. It's a real entity out there. So when we change our coordinate system, the basis vectors change and the coefficients change, but as a result, the overall things stay the same. So strictly speaking, the coefficients actually change in an exact opposite manner as the basis vectors. Thus the covector components, which transform oppositely to the components of a vector, are actually transforming in exactly the same way as the basis vectors do. This is the reason why they are called covariant. On the other hand, vector components transform in a manner opposite to the basis vectors. That is why they are called contravariants. So this old nomenclature was really with respect to the way the basis vectors change, and that is why you end up with this apparently contradictory nomenclature, where things which transform like coordinates are called contravariant, and things which transform opposite to coordinates are called covariant. Okay, now that we have spent quite some time in understanding the way in which vectors and covectors behave under non-orthogonal transformations, it would have been the proper thing to take a look at a very, very important example of non-orthogonal transformation. And we all know the one I am referring to, because we have already talked about that in the last lecture as well. It's none other than Lorentz transformations. Remember, Lorentz transformations are not really orthogonal simply because x0 square plus x1 square plus x2 square plus x3 square is not an invariant under Lorentz transformations. The invariant is somewhat similar but not the same as the sum of squares. It's x0 square minus x1 square minus x2 square minus x3 square. So Lorentz transformations are not orthogonal, although they are almost orthogonal. It's only a matter of a change of a few signs. So under the transformation x prime mu equals lambda mu nu x nu, or something which can be written in the matrix form as x prime equal to lx, vectors transform like a prime mu equals lambda mu nu a nu, with the indices placed such that the first index is on the top and the second index is at the bottom. So from the top left to the bottom right. And covectors transform like b prime mu equal to lambda mu nu b nu, where the indices go the other way. Just to stress that this is nothing unusual, this is exactly the convention that we had laid down for a general orthogonal transformation. In the last lecture, I told you that the indices on the lambda are placed in a particular manner, and I did assure you that you will understand why later. In this lecture, I hope I have been able to explain what is the point behind labeling the indices in this particular manner. Now, the behavior of vectors and covectors under Lorentz transformations is immensely important for physics. In fact, much of the theory of special relativity can be recast entirely in the language of 4 vectors and 4 covectors. Also, sometimes 4 tensors of higher rank, and this merits a much more detailed discussion. We will talk about this in some detail in the next lecture, but today let me just skip over to the next important topic, which is that of a general coordinate transformation and how does covectors behave under them. But before we go there, let me just point out one thing. The fact that a Lorentz transformation is very nearly orthogonal has actually prompted an attempt to make it actually orthogonal. Now, how do you do that? The answer is simple. In an orthogonal transformation, you need the sum of squares of the coordinates to be invariant. Here, what is invariant is x0 square minus x1 square minus x2 square minus x3 square, or equivalently minus x0 square plus x1 square plus x2 square plus x3 square. Now, one way to make this into a sum of squares is just to replace x0 by x4, which is I times x0, I being square root of minus 1. If you did that, in this new way of labeling space-time coordinates, where the temporal coordinate becomes I times ct rather than ct, you do get the sum of squares of the coordinates as an invariant, and so you can make the Lorentz transformations into orthogonal transformations at the expense of using a purely imaginary time component. This is exactly what Hermann Minkowski did when he first introduced the concept of Minkowski's space-time, and the advantage, of course, was he could get to use the standard results which were already there for orthogonal transformations. He could, in a sense, make the Lorentz transformations look exactly like rotations. However, the fact that you did have to use an imaginary time coordinate ended up making things rather confusing if you tried to push this analogy between rotations and Lorentz transformations too far. In most modern expositions of special relativity, this imaginary time component is actually rather frowned upon, for the simple reason that the advantage it imparts in giving you an orthogonal transformation to work with is far outweighed by the disadvantages that come with having to use an imaginary time. You will find several, especially older textbooks of special relativity, which use this ICT convention or x1, x2, x3, x4 convention for coordinate 4 vectors. And if you are using any such textbook, you will find that the equations differ slightly from the equations that we have written down here. Well, the basic reason why modern textbooks have mostly done away with this ICT convention is that when you go over to general relativity, you have to deal with a non-orthogonal transformation anyway, and this added I is not really going to save you there. So it is considered to be a good idea to get used to non-orthogonal transformations within the simpler arena of special relativity before you move on to the richer arena of general relativity. I will end today's lecture by talking about what happens under general coordinate transformations, which are exactly what you need in general relativity. As we had discussed in the last lecture, under a general coordinate transformation, where x1, x2, x3, xn goes over to x prime 1, x prime 2, x prime 3, x prime n in a smooth, at least locally invertible manner, it is the coordinate differentials which give you prototypes of vectors because they are the ones which transform linearly. So dx prime I is del x prime I del xj dxj, which is nothing but the standard chain rule that you meet in multivariable calculus. And that tells you that the new coordinate differentials are linear combinations of the old coordinate differentials. Just to make this look a bit more like the thing that we have been discussing so far, you can write del x prime I del xj as the ijth component of a matrix, capital J, the Jacobian matrix actually. So that means that dx prime I becomes capital J ij dxj. Now the only real difference which you get for the case of a nonlinear transformation, like the kind we are discussing now, and the linear transformations that we discussed earlier, is that here the jij's can actually depend on the coordinates x1, x2, xn. For a linear transformation, jij would really be exactly the same as the transformation coefficient sij. Now, as we had already seen before, vectors transform as follows. For a vector a prime I becomes del x prime I del xj aj, or you could write that as jij aj. In full analogy with the general case for non-orthogonal transformations that we had written down earlier. We will talk about what happens to covectors under such transformations. But to understand that, we should actually take a look at a covector, which is a very, very familiar one to all of us physics students. This is nothing but the good old gradient that we learned about in first year in college.
Now hold on a second. Didn't we always know that the gradient of a scalar is a vector? So how come we are calling it a covector? Let me explain. And also let me remind those of you who have forgotten it that the gradient of a scalar in an n-dimensional space is given by the following. It's an n-component object whose elements are del phi del x1, del phi del x2 up to del phi del xn. The n partial derivatives of the scalar field phi with respect to the coordinates. Now we denote this with a standard abuse of notation as del phi del xi, where of course del phi del xi could either stand for the object itself or for the ith component of that object, and it's the context which helps us decide what we are really referring to. Note that the differential of a scalar field d phi is obviously a scalar, and standard mathematics that we learned long time ago tells us that this must be del phi del x1 dx1 plus del phi del x2 dx2 summed up all the way up to del phi del xn dxn. That is, it must be del phi del xi dxi. And this implies that if you contract elements of the gradient with the coordinate differentials, you end up with a scalar. Now the coordinate differentials of course transform like vectors. They are the prototypes of vectors after all. And hence the gradient is a way of mapping vectors linearly into numbers. So this must be a covector. So despite having treated the gradient all this while like a vector, we now learn that it is not really a vector, it is a covector. And once again, the reason why we did not know this until now, perhaps, was simply because we were all dealing with vectors under rotations, and as I have stressed over and over again, under rotations, there is no difference between vectors and covectors. But now that we are dealing with general coordinate transformations, we have to live with the fact that the gradient of a scalar is a different kind of entity. Now, because it is a covector, it must transform using the matrix J transpose inverse. We are going to see that that is the case, but given the fact that this is a gradient, so it's really a bunch of partial derivatives, we know how it is going to transform when you change your coordinates. We will need to use nothing other than the standard chain rule for multiple variables. So how does this bunch of partial derivatives change when we change the coordinates? Del phi del xi goes over to del phi del x prime I. Actually, it should go over to del phi prime del x prime I, but the scalar function does not change, so we keep on calling it phi. There is a bit of a catch here. The function actually changes because you are expressing it in terms of new variables, but the value of the function doesn't change, and that is why we are retaining the old symbol phi for this. There is a sort of running battle between mathematicians and physicists as to whether this is the right thing to do, but being good physicists, we are going to actually stick to this notation that phi here actually stands for a different function in terms of x1 prime, x2 prime, xn prime, but we will denote it with the same symbol despite the fact that technically speaking it's a different function simply because it takes the same value. Be that as it may, what we end up with is del phi del x prime I is related to the original derivatives del phi del xj by this formula del phi del x prime I equals del xj del x prime I del phi del xj. So, whereas vectors pick up coefficients of del x prime I del xj under a coordinate transformation, the gradient, which is an example of a covector, picks up del xj del x prime I as coefficients. To check whether we have got it right, let us try to see how the differential d phi changes under a coordinate transformation. In fact, it should not change, And that was the rationale behind us deciding that del phi del xi, the gradient, should be actually a covector. So what really happens is del phi del xi dxi goes over under a coordinate transformation to del phi del x prime I dx prime I. Now we know that del phi del x prime I becomes del xj del x prime I del phi del xj, the term written in red there, and the term in the orange after that is the value of dx prime I, namely del x prime I del xk dxk. Once again we are using the summation convention, and we are being careful that the two dummy indices that we have introduced, j and k, are kept separate from each other. Next step, as always, is to move the del x prime I del xk across the del phi del xj, and this puts the two partial derivatives next to each other. Of course, it's not just a product of two partial derivatives, it's actually a sum over I after that, and that, according to standard rules of partial differentiation, becomes the partial derivative of xj with respect to xk. The rest of the expression del phi del xj dxk stays as it is. But now the partial derivative del xj del xk is obviously delta jk, and using the standard property of the delta symbol, this becomes del phi del xj dxj, which of course is exactly the same as del phi del xi dxi. So as promised, the differential d phi does not change under coordinate transformations, and that tells us that the transformation rule that we have selected for del phi del xi actually works out fine. Now, just as coordinate differentials act like prototypes of vectors, and the coefficients that vectors pick up when they transform are exactly the same as the coefficients that coordinate differentials pick up, the gradient acts as a prototype for all covectors. So any covector would have a bunch of n components, and these components would transform under the coordinate transformation exactly like the gradient. That is, a prime I would be del xj del x prime I aj. And just to check whether we have got this right, you can actually verify pretty easily that aibi is a scalar. Now, the proof of that is exactly similar to the calculation that we have just now carried out, so I'm not going to repeat that. It should be possible for you to verify on your own, just on the basis of properties of partial derivatives, that these two quantities, a prime I, b prime I, and aibi are exactly the same. So, the basic defining property of a covector, something which gives the number from a vector in a linear fashion, is valid here. In order to see the inner consistency of our results for the general coordinate transformation with the standard result that we have used for general linear transformations, let us now examine this result that we have been using so far. Del xj del x prime I del x prime I del xk is nothing but del xj del xk, and that is nothing but delta jk. Now, del x prime I del xk is the ikth element of our transformation matrix capital J. Remember, these are the coefficients which dxi pick up when you carry out a coordinate transformation. Now, since delta jk is the jkth element of the identity matrix, and you are summing up over the index I, which is the row index for jik, this will become a matrix multiplication if we treat the preceding factor del xj del x prime I as a jith element of a matrix. And that matrix is trivially J inverse, because the matrix multiplication of that with J gives you the identity. So del xj del x prime I is a jith element of J inverse, or the ijth element of J inverse transpose. So the coefficient of aj in the expansion of a prime I del xj del x prime I is nothing but the ijth element of J transpose inverse, and that, written in matrix language, treating the components a1, a2, an of the covector as a column vector, would simply be a prime equal to jt inverse a. So this shows us that even though the expression for general coordinate transformations looks slightly different from the expressions for linear coordinate transformations, they are actually not that different. They both essentially say the same thing, except for the fact that for general coordinate transformations, the coefficient matrix can change from place to place. As we have said earlier, the most common place where we are going to use general coordinate transformations, or rather tensors and scalars and vectors under general coordinate transformations, is general relativity. The theory is exactly the same there as far as the definition and transformation law for covectors and vectors are concerned. The only point that I would like to remind you is that the convention that we use there is that the indices run not from 1 to n, but specifically from 0 to 3, and typically in such situations we use Greek indices and not Latin indices. So a vector transformation rule looks like A prime mu is del x prime mu del x nu a nu, where nu is going to be summed over from 0 to 3, and the covector transformation rule looks like A prime lower mu is del x nu del x prime mu a lower nu. A quick way to remember what goes where is simply this. If you have an upstairs index on the left, then the new coordinate has the same index in the derivative on the right. That is, A prime upper mu has del x prime mu del x nu as a coefficient, and A prime lower mu has del x nu del x prime mu as a coefficient. That is quite enough to decide exactly what the partial derivative is going to be. Now, as I have already said, in this lecture we have skimmed over the subject of covectors under Lorentz transformations. While Lorentz transformations are just a special case of the general non-orthogonal transformations, there are several special features which make a study of them rather important, especially in the view of the fact that they will be extremely useful in the study of special relativity, and the experience that we will gain from that will also become very important when we want to use this for the more complex arena of general relativity. So in the next lecture, we are going to take a deeper look at covectors under Lorentz transformations. It will also, as an added bonus, give us another way of understanding why the coefficient matrix elements for the covector transformation is written in that peculiar manner, from bottom left to top right. Once we learn about how to use the metric to raise or lower indices, this particular way of writing the coefficient will become sort of obvious. We will also introduce tensors of higher rank for the first time in the next lecture. But all that will be later. Goodbye for now.